So I'm going to talk to you today about a project that I've been doing for a couple of years now. We started this work back in 2014 with my colleague Suzanne Boxman, who got her PhD working on this work and now is off working at EPA in Washington. And so first, since I'm the first speaker in aquaculture, I get to talk about why we need aquaculture, and it's certainly critical that we increase aquaculture production in our country. Currently, over 91% of the seafood that we eat in this country is imported, even here in Florida, where we've got all these wonderful resources surrounding us. And of course, the majority of that aquaculture production is taking place in Asia, with over 89% of the seafood being produced there, followed by the Americas, but that's not the U.S. That's primarily Central and South America, and in Canada, where a lot of shrimp and salmon is being produced. And then Europe has really expanded their aquaculture production over the years. They're right behind the Americas, and Africa is increasing their production. Now they're up to 2.3% of the world production. And I was so sad to see when I was looking up the statistics for this presentation that our seafood trade deficit is now up at $14 billion in the United States. All my presentations before said it was at 11, so now we're at 14. And we rank 17th in terms of aquaculture production. So we have a huge opportunity, especially considering that by the year 2030, we predict that 62% of the seafood will come from aquaculture. We're right now at about 50%. So we're going to see it increasing, and let's hopefully have some of that being done here in our country. And of course, the big challenge, and the challenge for our young students and young scientists, is to determine how we are going to feed our ever-growing population, with the population projected to reach over 9 billion people by 2050. And it's not going to happen with land-based agriculture, where we see that it's already flattened out. Plants and land-based ag has already flattened out in terms of production. Fisheries is flattening as well because we've already reached our maximum sustainable yield. And so where is it going to come from? It's primarily going to come from aquaculture. And currently, most of the production is in freshwater, but we're going to have to shift to saltwater production, mainly because of limited availability of fresh water as our population continues to grow. So the question is, how are we going to do that without damaging our natural resources and damaging the environment? The other thing that is often misquoted, because people are using old data based on feed conversion ratios, is that fish is by far the most efficient way to produce protein. It takes only 1.1 pounds of food to produce 1 pound of fish. And so I often hear people talk about this outdated salmon figure of 5 pounds to 1. That is not correct. We have greatly improved the technology. It's now 1.1 pound of food to produce a pound of fish, but 6.8 pounds of food to produce a pound of beef. So you can see that it's the most efficient way to produce that protein. It's also a better source of minerals and vitamins, and it is the most nutritious source of protein, in that it lowers your risk of heart disease, it improves your brain function, and it reduces obesity. So there's a lot of good reasons to eat seafood, and that's why doctors are encouraging us to do that. So I keep searching for where the right model is. How are we going to increase seafood production? Because my friends that are here know that I've been talking about this now for a very long time, and I still see us not moving into this area in the U.S. And so one area that's gotten a lot of interest, and Laura's going to talk about this a little later in the session, is aquaponics production. And most of that work is being done in freshwater systems. And that technology was developed quite some time ago, but it is now taking off. It's got its new life and moving up in the field of interest. And the primary product that's being produced in those systems is the fish tilapia. and then a variety of different freshwater vegetables are being produced using that technology. But there are still questions about the economics of those production systems, and I know a lot of people think that it's mainly a way for aquaculture supply companies to make a lot of money on equipment. And that's mainly because of the boutique type nature of the systems that are out there. But we're seeing a number of commercial entities scaling up, and we're going to know much more about the viability of that technology as time goes on. So my area of research is not in the freshwater area, it's in the marine area, because I am concerned about water resources and our ability to produce food in the future. And so I focused on saltwater production of marine vegetables or halophyte plants together with marine fish. And so there's been very little research in this area, and the systems are much more complex to operate. And there's a big question about what kind of vegetables are we going to produce in those systems. There's been some work done with Salicornia, a common wetland plant, especially in Israel, in Arizona, and in some areas in Southeast Asia. That plant has been produced and used as food both for people and for animal fodder. But the question is, what can we do here, and where are the species that we're going to work on? And so this is our facility out at Moat. We work on a wide range of different topic areas, everything from marine fish production systems to the development of the marine fish technology itself, especially maturation and spawning technologies. Our aquaponics system is located in a greenhouse right here next to our metal buildings, which didn't get damaged in the hurricane, thank heavens. We did have some damage, but not to that particular unit. And what we did is, when we were focusing on this project and trying to determine what we were going to do, our goal was to make our aquaponics system more fish-focused and less vegetable-focused. Most of the freshwater systems are 90% vegetables and about 10% fish, and I'm really interested in protein production, and also I'm working on halophyte plants, which is a whole new market to develop. And so I really wanted to see what could we do, how can we pull in some of the recirculating aquaculture technology that's been developed in the last 20 years and use that in combination with the aquaponics technology to create a food production system that will work economically. The other thing that I'm working on is trying to figure out what size system is going to be acceptable to our communities here in this country. We have a lot of resistance to developing aquaculture, and that's why we haven't seen it develop well. And so I've learned, as I've been working on this project, that one area that is there's a lot of enthusiasm about is smaller scale local food production units. So our effort was focused on a smaller scale production system. We developed a prototype, not a commercial scale unit, but a prototype using red drum and two different edible sea vegetables, sea purslane and saltwort. And this system, here's a diagram of the setup. Here's the fish production, filtration, and vegetables up here in the upper portion. Included these fish tanks, and you can see here, this is a great picture because it really shows the way the system was designed. The fish tanks are the highest point in the production unit, and everything else flows down from there. So we can take advantage of gravity and still incorporate filtration systems. But what I wanted to do is take simpler technology that we've used in most of our RAS units, something that people could use on farms and wouldn't break the bank in order to build the system. And so here's my solids filtration unit. We've got two different types of solids filters, a biofilter, and here's the plant production systems. And everything here is flowing by gravity until we get back to the sump. And at this point, we're then going to pull out the water and send it back to the fish tanks using that setup. Now, we also have to deal with solid waste. So here's my solids filters, and I'm going to collect those solids through backwashing and send it into a sand drying bed This is the favorite part of visiting the facility for grade school kids. They like to talk about fish poop, so they love to hear this part of my talk. And so here's where we're collecting the fish solid waste. The water is percolating through that system and then going into this tank and pumping back through the filtration unit. So this prototype system was designed and constructed in 2014. We did our first production trial in 2015, and since then I've completed a whole trial in 2016, and I'm in the middle of my third trial. So let's talk about results. The sea vegetables. This was the first challenge, is what am I going to grow in these systems? I'm working in about half-strength seawater, so about 15 parts per thousand, and I have to have plants that are growing in there that can go into the markets. And so I looked at what was out there that was edible and came up with these two options. And so those vegetables are then being marketed into farmers markets, through local restaurants, and through sustainable chefs. And what we determined is that the purslane was by far the most efficient and effective plant to produce in that system. We could produce a whole raceway of plants every 30 days. And we are constantly pruning and marketing product out of those raceways throughout the year. It's available year-round. The second product, the saltwort, it took me much longer to develop the technology for that plant. It does require more nutrients than we had coming in because we have some filtration on the other side. And also there appear to be limitations in its growth rates in these hydroponic systems. So that's still one that we're working on, but you can see in this picture right here that it does do pretty well once it gets off and running. It just takes about 6 months to get everything up and operating. I've also attempted to grow Salicornia and sea rocket, but those are both more difficult species. You have to start them with seed. They don't do as well in these systems. So we're still working on our production methods, thanks to the master gardener that's working with me on this project. The other aspect is getting it out and developing those markets. And so we've done that through a variety of different venues, both reaching out to our local community through Eat Local Week and partnering with chefs such as Steve Phelps right here, who is a local chef at our restaurant in Sarasota, who's really interested in getting sustainable seafood into the markets. And he's been super helpful in helping me to get the sea vegetables accepted and educating consumers on those products. Then, of course, there's the fish. So we have to have, this is my whole focus, is fish production. And so in 2015, we had really great results. We stocked the system with 5-month-old fish and had reached market size at about 13 months, but every year we've improved our production. So in 2016, we stocked them 2 months earlier and were able to get them out a month sooner to the markets. And this year we stocked them at 2 months of age, and we've already got 1 pound fish at about 6 months, so we expect to beat that record this year as well. And so this is just showing the growth in the 3 different year trials. And on top of that, our densities are also increasing each year. We were up at 31 kilos per cubic meter in the first year, 48 in the second, and I expect we'll top out at about 48 this year. Kilos of fish per cubic meter of water. And that's what it's all about, is in terms of how much production are you going to get into those marketplaces. Also, we definitely demonstrated that we could produce multiple products. In other words, we achieved exceeded the maximum design density, which is 21 kilos per cubic meter of fish for the RAS portion, and the rest of it's going into fish production. So in conclusion, the system does support multiple products. You can produce 3 different edible sea vegetable products and market them into local markets. You don't need to exchange any water, and the way that we do that is by utilizing our sand drying bed for denitrification to reduce the nitrate levels, because when you have a 100% recycle system, you are going to build up nitrate very quickly. And so we use that to denitrify, and we are able to exceed the production capacity of a RAS system, allowing us to produce 2 different products, increasing the income level for the farmers. So now we're trying to figure out what is the appropriate size for the unit that will make economic sense. And again, we really wanted to create the minimum size unit that will create a marketable product and allow farmers to make a profit. So we're working on scaling it up over in Hardy County with some commercial partners that we've partnered with, and also working on looking at the production economics. The other thing we need to do is expand the market for halified plants, so that's another focus for future efforts, and also find a way to better address using the saline solids that come out of that system. We use some of it to grow wetland plants, but that's not the long-term solution because there's too much fish poop coming out of those systems. So we're looking at everything from mineralization to energy production using the solids. And I want to acknowledge my funding agency, of course, Florida Sea Grant, who really helped us to get all this going, and a variety of different groups that have contributed along the way. Thank you.